Okay, starting new chapter, chapter 7. Chapter 7 deals with functions with exponential growth, exponential decay. It also does things with logarithms and natural logs. But to start with, we're going to talk about graphing exponential growth functions. And exponential growth functions are functions where the variable is our exponent, and our the value that they give us, which is represented as b, is greater than 1. So it allows whatever x equals to grow exponentially. It gets exponentially larger, exponentially smaller, depending on how large your x is, whether it's approaching, a really big positive number or a really big negative number. Things to keep in mind um, is that it rises from left to right through points 0, 1, and 0 and 1b, and the uh, the asymptote is the x-axis. Asymptotes are it's a value that you're going to get really, really close to but never reach. So as you can see, if you look at this particular graph here, this graph is swooping downward like this, and it looks like it's trying to approach uh, x equals 0, but it never will. So that's what asymptotes sort of mean. So today, basically, what we're trying to do is we're trying to graph these functions. Um, you can always, just make your t-chart, and you can use positive and negative values. So I have a -3, a -2, -1, 0, 1, 2, and 3. And if you substitute in x in for these values, you're going to get a y. You're going to get like 0.008, 0.04, 0.2, 1, 5, 25, and 125. So if I plot these points here, that's really small, a little bit bigger. 0 is 1, 1 is 5, 2 is 25, somewhere up here. So kind of looks something kind of like this. For the most part, we're dealing with the domain, which is the set of x values. We're just going to have the set of real numbers. For the range here, um, your y is not going to be negative, nor is it going to be 0. So your y is going to be greater than 0 in this case when you have a positive value here. So, but if you don't like doing the t-chart here, there's only really like 3 points that I'm really concerned with. I'm concerned with points 0 comma a, 1 comma a times b, and -1 comma a times 1 over b. So if I look at this example here, this is my a is 1/3 and my b is 3. So first off, I'm just concentrate on uh, 1 comma a, so it'd be, or 0 comma a, which would be 0 comma 1/3. The next point I'm looking for is 1 comma whatever a times b is, which would be 1. And the last one would be -1, and then it would be a times 1 over b, so it would be 1/3 times 1/3, which would be what, 1/9. So I could plot these points. So I go -1, 1/9, so that's about right here. 1 and 1 is right here, and then 0, 1/3 is right about there. So then I can make my graph. My domain and range. Domain is all real numbers. My range, again, is y is greater than 0. Looking at example C, my A in this case is -1 because of that negative value. My B is 7/2. So I'm going to look at 0 comma A, which is -1. My next one is 1 comma whatever A times B is, but that would be what, a -7/2. And the last one would be -1 comma whatever A times, so it would be what, -2/7. So I'll plot these points. I got 0, -1. I got 1 comma -7/2. So that's what, like 4, 3.5. So right about there. And -1 comma, so something like this. So then it kind of looks, the graph kind of comes right here. And that makes sense because we had our A was negative. So that means it's going to be shooting downward. And as X becomes larger, my Y is going to be like approaching -infinity. My domain here is all real numbers. Now, since that my range is, it's because it's negative, my Y is going to be less than 0. Here we have translations that which are very similar to what we dealt with when we were dealing with other functions. This is, so like the general equation would be y equals a times b x to the minus h plus k. So you're going to do the exact same thing. First off, you're going to uh, graph it like there's no h or k involved. And so you're going to be doing the exact same things as you did before. So I'm gonna look for those certain points. I want to find what 0 comma a is. In this case, a is 2. And I'm looking for 1 comma a times b. A times b would be 8. And the last one was -1, and it'd be a times, so it'd be 2 times 1, so that'd be what, 1/2. So I can plot these points. So I got 0 comma 2, 1 comma 8, and -1 comma 1/2. So with those plotted points, I can now do my translations. H, again, is the movement from right to left, and K is my movement up and down. So my H here equals a -2, and my K is a +1. So that means I'm going to move it to the left 2, so I'm going to look at this point. I'm going to go 1, 2, 1. So my new point is up here. Again, with going at 0, 2, 1, 2, up 1. 1, -1/2, so I'm going to go 1, 2, up 1. So that's where my new graph is. And if I had a domain and range, my domain would still be all real numbers, and my range would be y has to be greater than 1. And your value of k will help you determine what that range will be. All right, let's go to a story problem. I got two different formulas for you. This first one is about exponential growth. The second one is about compound interest formula. The exponential growth one means if we have an initial amount A, and we have a rate of increase, which is R, which is usually a percentage, and then we have a period of time. So if we have this example here was they want me to write an exponential function to model the situation. They want me to estimate the value of the function after 5 years to the nearest whole number. They want to know the population of 290 animals that increase at an annual rate of 9%. So I'm going to plug it in. So y equals my initial rate, or my initial amount is 290. So I'm going to go 1 plus my rate is at 9%. So I got to remember to write that as a decimal. And then in this particular situation, they want to know what it is within 5 years. So my t would be 5. And when I do all the math to the nearest whole number, I get roughly something like about 446 animals. For the compound interest, again, R is your interest rate, which is a decimal. Usually it's a percentage. N is the number of times it's compounded. Usually what that means is how many times it's compounded in a year. So if they say it's compounded daily, your N would be 365. If it's compounded quarterly, it's 4. Compounded monthly, it's 12. Compounded yearly, it's 1. The time is how many years they're looking for. P is the initial principal, and A is the amount. So if I'm going to write an equation for this example, where I need to find the value of $1,000 deposited for 10 years in an account paying 6% interest annually. So I have A equals my P would be 1,000. And then I have 1 plus my rate would be 0.6 divided by, now this is monthly. So if it's monthly, that means that my N is going to be 12. And I'm going to go it's to the N times T, so it would be 12 times 10, so that would be what, 120? And when you do all the math, it comes out to be roughly $1,800, 19, is it 18, 19, and 40 cents. The second example here is they want you to know is how much money must be deposited. So they don't know what the initial principal is, but they want to have a balance of $1,000 after 10 years. So your A is 1,000 equals, we don't know what P is, but we have 1 plus, we know what the rate is 8%, and it's quarterly, so that means we divide it by 4, and they want to know it after 10 years, but we have N times T, which would be 40. So that means that we have 1,000 equals, do the math here, roughly 2.21 P. Solve for P, it equals roughly 452.49. And that is being able to solve functions through exponential growth. Hope this helps. Until next time.